Okay, I suppose we'll get going. So I don't actually have any announcements because the quiz was already due. Um, I think most everyone here finished it in class. There's not too many online submissions, but um, yeah, nothing really to say there. I haven't had a chance to really look at it yet. I've sorted them, alphabetical order, so that counts as starting them. I will have them back by Wednesday, just because that's how my schedule lines up. So that will usually be the case. Yeah, not much else. So I guess we'll just jump straight in. So last class we talked about truth tables and how to build them. We just did several examples, and it goes to kind of showing that math is not a spectator sport, right? That this will happen generally in this class where you'll sit through the lectures and you'll be like, at least a little bit, you'll be like, I don't know if I know how to do that. And then you'll actually sit down to do an exercise and you'll be like, okay, actually, I'm starting to get it, right? Especially when I answer your questions. And then by the end of it, you'll do like one or two and you'll be like, okay, good, got it. There shouldn't, so with the removal of the proof section, there shouldn't be too much in this course that just makes you go, no idea, right? That section definitely made students do that. And so that's why I'm taking it out. But yeah, we just talked about how to build truth tables. And I also talked about the concept of what it means to be a tautology, which is essentially just, we're going to use it to mean equality, right? You can interchange both sides of specific tautologies with each other, and that's what I'm going to start with. They give us identities. And it just means that the truth table, if you built it, is all T's at the end of it, right? Just every single thing is a T, so it's never a false statement. So I'm going to just open with this. The following are all tautologies. Now, you don't have to write this down unless you want to, because it's a big list, and you don't have to memorize it, because if you're working on an exercise that needs them, then you've got the list. But if you like to handwrite them, if that helps you remember them, then feel free to. So we did have one of them last class. So we had P is equivalent to not P, right? And this is called double negation. So I mentioned this about tautologies. The important thing here is if we have this symbol, it means we can interchange these two things, right? So we can simplify in a sense. Like again, barring that word having a loaded definition. But like if we saw this, then most people would agree removing those symbols makes it simpler, right? So we could just turn this into this, right? That's kind of the point of these tautologies. They allow us to make our logical statements look simpler or more convenient, as with these ones. So we've got P and Q is equivalent to Q and P. That's not that surprising if you just think about the truth tables, right? Doesn't matter what order you do them in. P or Q, same thing. Q or P, right? This is called the commutative law. Which is exactly, that's what we call it in addition too, right? X plus Y is the same thing as Y plus X, right? That's called the commutative law. We also have the associative law. So what this says is that if you have brackets, it doesn't matter which order you write them in, right? And that's also true for addition, right? X plus Y plus Z, you can do it in any order, right? Technically, there's brackets there in a mathematical sense, but it doesn't matter which order you do them in. And that's all this is saying. Now, the important thing, this is something that students often get mixed up because there is the concept of distributive. These are the same, right? So if these are different, that's a different rule, right? So we have to make sure these are the same symbol for this rule to apply. So this is called associative law. And of course, it's also true for or, P or Q or R. Makes sense. These are pretty similar statements. So I just said this is for when they're the same. There is a law for when they are different symbols here, and that's called the distributive law. So I will write it this way. P and Q or R. So I'm going to make a note of that. These are different now. So it works sort of like we have for if this were, X times Y plus Z, it works in a similar way. So this sort of distributes, right? You might remember doing that in high school with the arrow and stuff like that, foiling and whatnot. This is basically what gives us that. So P, the outside one hits both of the inside ones. P and Q or P and R, right? So this is called distributive. And there is also one for the other order. Again, or on the outside and on the inside. P or Q and P or R. Right, so again, different symbols here, same symbols. They're different rules. So this is the most common mistake that students make. They just get these mixed up, right? It's easy to get lost in the sauce. There's a couple more in here that I probably won't write down just because we're not really going to need them in terms of algebra. So this one here is an example of what I mean. There's even more that I didn't even write in this list. So we have P implies Q is the same thing as not Q implies not P. This is called the contrapositive. It's useful for a proof technique, which you don't have to worry about. But it's a common way to argue logically. These are the same thing. So what this is essentially saying is start with a true hypothesis, see what happens with your conclusion. Start with a false hypothesis, and then if you prove that the hypothesis is false, then you've actually reached it works out, right? So if you build the truth tables for these things, you'll see that they're the same, which is all that matters for seeing that this is the important statement. This is also a useful law. It's called the absorption law. So again, this is important. These are different symbols. So it's P and P or Q. It turns out this is just the same thing as P, right? This is a really useful one because it means if you have this more complex thing written down, you just write P instead, right? And the same is true if we sort of swap symbols. Same thing as P. This is called absorption. Couple of other things. These aren't really rules so much as it's just a convenient place to write them. So P or not P. Makes it sound like Shakespeare, but what do you think? What do you think this is equivalent to, right? Yeah, this is always true, right? If P is true, then it doesn't matter. This is a true statement. If P is false, then not P is true, which means this whole statement is true. So it's just true no matter what P is. So this is a true statement. So every time you see this, you could just replace it with it's just true, right? There's no name for this. I mean, I could come up with one probably, but similarly, P and not P, the opposite, right? If P is true, then not P is false. If P is false, then not P is true. So either way, it's false. So these just give you a convenient way of simplifying statements, right? If you see, oh, I've got this written down, then you know it's just true, and then that probably just collapses a bunch of stuff, right? Because if you had P and a true, always true statement, that's just P, right? The true statement doesn't matter at all. Similarly, if you had P or false, you can get rid of the false, right? Because then the false doesn't matter. It's just whatever P is, what that is. So the point here is, these look like algebra rules. Right here, negative x is x. X plus y is equal to y plus x. X plus y plus z is equal to x plus, or I did that in y plus z are the same thing, right? These are things that we know. I mean, this one you probably don't even think about, right? Because it's just, you say, well, that's always true. For addition, yes. Not true for every operation ever. There are mathematical operations where even this rule fails. This one's more common to fail, though, and we're actually going to talk about one. So we can't take that for granted. So the fact that it's true is nice. This one here is if you have x times y plus z, that's x times y plus x times z, right? Distributive law, foiling, if you want to call it that. These don't really have mathematical equivalents, but the point here is the reason why we would care about these is to just simplify things, right? This tells us, hey, we don't care, so we don't need brackets, right? It says, hey, we don't care which order you write them in, so write them in the way that looks the nicest or is most convenient for you, right? This is saying, hey, you can go from this to here or here to there. So going from here to here, you would call that distributing. Going from here to here, you'd probably call it factoring. But the point is you could do either, right? That one might be simpler than the other depending on context. And we could do that with our logical rules, which is nice. But there is one that we're missing here. And I saw some people playing with it a bit. And we're gonna talk about it. Maybe not today, maybe tomorrow or Wednesday. But what happens if we put a negative sign in front of this, right? Like what if we talk about not P and Q? So we actually build the truth table for this. It's a little more complicated. It's called De Morgan's laws. It doesn't work exactly how you expect. But we've got a lot of rules, right? And you don't have to memorize these because they're all just in the notes. So if you're working on a problem that's like, okay, I need to simplify some stuff, then you've got them available. Okay, but before we get to that rule, there is another concept I want to introduce. And they're called quantifiers. So one of the things we have here is variables associated with these statements, right? But when we have a formula that has a variable in it, we have to declare that variable what it is, right? We'd say like, okay, well, X is Travis or X is 5, whatever is appropriate, right? But we maybe want to make broader statements than that, right? We might want to say for all possible choices of X, right? Instead of just for the specific one you gave me, right? That's a much more powerful statement. If I can say for all choices of X, this is true, then obviously that's way stronger than for the specific one you gave me, right? And that's what quantifiers let us do. So let me just write this down. Consider the following. So X is less than or equal to 5, and X is bigger than 3. So essentially, X is between 3 and 5 inclusive with 5. So whether or not this is true depends on a choice of X. choice of x dictates whether this is true. Okay, so like as an example, x equals 4. True. Right? X is bigger than 3 and it's less than or equal to 5. X equals 6. False. Right? That's bigger than 5. So let's consider an alternative statement. Instead, for every x, x is less than or equal to 5 and x is bigger than 3. Is this a true statement or a false statement? Right, because what I'm claiming here is for no matter what value of x you pick, this is true, right? But that's obviously not the case. So we contrast this with this, where this is true or false depending on choice of x. This one here has an x in it, but it actually has a definite truth value, right? It no longer depends on x. So this for every x has sort of specified x for us, but just way more broadly. This is false. But what about there exists an x such that x is less than or equal to 5 and x is bigger than 3. Is that a true statement or a false statement? Yeah, right? Because this is just saying there is an x, right? There is one. I didn't say how many, right? There just is one. Yeah, we found 4, right? But because there is one, this is now a true statement, right? So these right here, in terms of English, are quantifiers, right? They sort of allow us to more broadly define a statement that, so like something with a variable, we will now make the variable, I don't want to say irrelevant, but the statement becomes stronger, right? Than whatever it was we were saying originally. So the phrase for every x is called a universal quantifier. Universal because, I mean, it's specifying all of them, right? Just everything possible, right? This is denoted because, of course, in math we want to, I mean, there exists an x such that sounds really obnoxious to write literally every single line, so we come up with shorthand for it. So it's an upside down A next to your variable. So this is saying for every choice of x, whatever follows. Okay, this one here there exists an x such that which is a mouthful. It's called an existential quantifier and not like an existential nightmare like probably a lot of people think math is. I make that joke every term. Nobody laughs at it. An existential quantifier. Okay. So this is denoted by, well, for this, the universal quantifier, we use an upside down A. So what are we going to use for existential? That's actually it's not that, but that's a smart response because the one I'm expecting is an upside down E. And it's like, well, that's the same. It's not an A. Normally, it's a backwards E. We want to kind of do the same idea, but we can't do an upside down capital E because they're the same. So we just flip it in a different way. So this is red. This is a very shorthand notation for there exists an X such that, right? Or I can find an X so that, or some kind of rephrasing of that, right? There is an X that exists. I'm not telling you which one it is, but there is one. And with that X, the following is true. So this, or these, allow us to assign definite truth values to formulas involving variables. Okay, so let's dive into these a little bit more. And more just it's more just like how to read them, because a lot of the struggle with these sorts of statements is that you've got the symbols written down, but then you're like I can work with the symbols, but like what does that actually say, right? And sometimes that can be challenging to interpret. So let's focus on universal quantifier first. So that's the upside down A. So the sentence or formula, at this point it's a sentence in terms of our definitions. Upside down A x P of x is true if and only if, which is, that's another phrase for that. So basically, these are equivalent to each other. You can say either one. It's true if and only if P of x is true, no matter what x is chosen. So an example, let's see if these are true or false statements. For all x, x squared is bigger than 0. So is this true or false? So let's think about what this is saying. So this is kind of what I mean, where it's like when I write it down in symbols, it's kind of like, but then when we actually write it down in English, it usually becomes clearer. So what this is saying is, well, for all x, x squared is bigger than or equal to 0. Or if you square x, the result is not negative. So when I phrase it like that, is that a true statement or a false statement? Yeah, right. I mean, well, again, if you say, well, what about complex numbers? Well, yeah, fine. But I mean, most of us are going to work in real numbers, right? So if you square x, the result is not negative. That's a true statement, right? So we would say, okay, that's true. How about this? To just give an example of so that's right here. What is this actually saying? It's saying for any choice of x and any choice of y, or any choice of x and y, right, independent of each other, you get to pick either of them, the result of x plus y is the same as y plus x. Well, that's true, right? We know that's true, right? That's 5 plus 2 is the same thing as 2 plus 5, right? We know that's the case, but this is just saying it doesn't matter what numbers you pick, it's true all the time, right? So this is also a true statement. But you can kind of see this disconnect here, right? The symbols, yeah, sure, they're nice and compact, but it takes a lot of practice to be able to read what that says in English. So it can help to just literally transcribe what you see with the definitions. So if you write for every x and for every y, x plus y equals y plus x, and then that helps, break things down a little bit. Here, for every x squared is bigger than or equal to 0, and then you're like, okay, well, what is that saying? It's saying if I take a value of x and then square it, is that bigger than or equal to 0? Yes, of course, right? So then you can start thinking about what this is actually saying. So this is normally found in mathematical statements, right? You can just think like a formula on a formula sheet, right? Generally, this symbol there is probably there even though we don't write it, right? So that's the thing with these symbols. They're often there in the background. We just don't write them. So this quantifier for all x is usually found in formulas or theorems or proofs or that sort of thing. Oftentimes, we don't even write it. Right? Because if you wrote down a formula on your formula sheet, the assumption is that it's going to be true for whatever you plug in, right? You better hope so, otherwise it's not a formula anymore, right? Okay, so let's do another example, but sort of going the other way. Right, let's, instead of translating from this to words, let's take words and then translate it into these symbols. So consider if x is negative, so is its cube. Okay, so when we're seeing this, so this is kind of what I mean here, right? We don't even write this symbol usually. We don't say for all x this is true. We've kind of omitted it, but I think the statement here is if you take a negative x, then it's true for all of them, right? Like no matter which negative x you choose. So this usually means, and if we meant something else in a different context, we would be very explicit and specify that. For every x where x is negative, then x cubed is negative. Okay, so that kind of helps us put this into symbols, right? Because for every x, okay, well, that's our quantifier, right, for all x. And what we're saying is x is negative, right? Or You could do less than or equals to there, whichever. Now we're saying for all x, if this is true, then x cubed is negative. So that if then is this symbol implies, or the conditional, x cubed is also less than 0. Right? That's what this is saying. If x is negative, so is its cube. For all possible choices of x being less than 0 means x cubed is also less than 0, right? So, like I said, it takes some getting used to go back and forth here. Generally speaking, in math texts or something like that, you won't see this language very much. Like you won't see the symbols again unless you're reading like very specific logic textbooks. So for our purposes, I'm not going to write this symbol all the time, right? I know there are probably lots of math classes you've taken where I would say, hey, this is what that symbol means. I'm going to use it literally all the time, right? Technically, it would probably make a lot of the stuff I write shorter, but then it also obfuscates the information. So not going to use it so much, but it's important for De Morgan's law so that I can explain some stuff with it. So that's why we're covering it. It's just how it works out with negation and stuff like that. Okay, so that's the universal quantifier. So let's really quick talk about the existential quantifier. So the sentence funny reverse E x P of x. So this is true if and only if. So again, these are equivalent statements to each other. There is at least one value of x so that P of x is true. So how many? Don't care, right? At least one. Is there 2, 5, a billion? Who cares, right? Doesn't matter. If there's only one, well, there still is an x. That makes it true. So you can kind of see that this statement, the universal quantifier, is very strong, right? It's saying, doesn't matter what you pick, it's true. This is kind of a weak statement, right? It's just saying, I found one. It's saying, well, great. Are there others? Oh, I'm not telling you, right? So it's still stronger than a statement written down and I'm saying, you go pick some x's. This is saying, well, at least there's one that works, right? So how about this? So is this true or false? I mean, generally speaking, when we think about it, we usually think squaring is an operation that makes things bigger, right? Right? 4 is bigger than 2. 9 is bigger than 3. So is there a situation where the opposite happens?
If it's negative.
So no, because that would be -2 bigger than or equal to 4.
Fractions?
Yeah, so it's fractions, right? So if you think about this, 1/2 is bigger than or equal to 1/2 squared, which is 1/4. Right? So when you have something that's less than 1, this sort of works in the opposite order. But the point is, I just wrote one down, right? I just wrote one down where this is true, which means this is now a true statement, right? Are there others? Who cares, right? This is true And I don't even need to qualify it more, right? I found one, good enough. It works for x equals 1/2. Here's another one. There exists an x and there exists a y. So that means there is an x and a y. Let me put a 2xy there. True or false? Right? So something that's interesting here is these statements. So if I just said, if I didn't have this, I was like, pick a value of x and y. It's not that bad, right? You just pick a value of x and y and see what happens. These statements, even though the existence of just one isn't that much stronger, it is still stronger, which means it's hard to actually prove these sometimes, right? So in this example, well, not this one, well, kind of this one, this is just like a known fact, right? This is a property of cubing, right? It keeps the same sign of whatever it was. But in general, these statements are hard to prove too, because the claim is it's true for all possible choices. Well, how many real numbers are there? Yeah, infinite. In fact, there are infinite integers. There are also infinite real numbers. They are not the same size of infinity. Real numbers have a metric ton more numbers. It's called the cardinality of the continuum, nerd stuff. But the point is, there's a lot, right? So if you're trying to prove it for all, that's a very strong statement, right? You better be pretty sure of yourself that someone isn't just going to say, well, have you tried this number, and then it doesn't work. Similarly here, you're basically trying to find a needle in a haystack, right? I'm trying to find just one that works, but now you're searching for that. So this is, I think it's a hyperbola or something like that. It is true. So we just said x equals 1, y equals 1. 1 squared is 1, plus 1 squared is 1, so that they add up to 2. 2 times 1 times 1 is 2. So that's a true statement, right? So I think this looks like, if I remember correctly, or something similar to that, right? It's some kind of graph. But the point is, these statements are not trivial to prove, right? So this quantifier is usually found, sort of hidden in the dark there, with statements like, if it's true for P of X, then it's also true for Q of X, right? So this quantifier is usually found like, if some X works for P of X, then it also works for Q of X. So this would be like, I don't know, algorithms in math, right? You're going through a process, right? You do one step of the algorithm, it produces some value. That value will also work in the next step, and so on, right? So this lets us do that sort of stuff. So kind of the point here is this is very formal, but at the end of the day, these are things that we talk about in math all the time, right? There is a choice that works, and then the other one is it works for all choices, right? That's the punchline of it, right? Okay, so I needed these because I want to talk about De Morgan's laws. So what De Morgan's law is, or I guess it's laws, there's technically two of them, two of them, is it tells us how to deal with negation in various formulas, right? How does the negative distribute into formulas? And it's not exactly natural, I don't think, if some formula P is given, then not P, sometimes called the denial of P, which again is important for logical arguments, right? If someone says P and you're like, not P, you're denying that person's statement, right? You're saying, no, the opposite. I don't want to say opposite because that's also not technically true. So De Morgan's laws are the following. And it basically tells us how does this negation, or how do we deny statements that involve and or. Not P and Q is the same thing as not P. Then we got the not Q there. And the natural thing is to say, well, it works like that, right? That's not what we need. It's or, right? It flips that sign. And same thing with the other one, P or Q. That's the same thing as not P and not Q. So we can actually check this, right? We can check with a truth table, right? We'll just check one of them, but it's relatively straightforward. Check with a truth table. So we've got our P, and we've got our Q. The usual stuff. And so we've got P and Q, which is P, F, F, F. And then we form the negation of that. So that's F, T, T, T. Okay, that's sort of the left-hand side there. So a lot of people will do this in your head. I'm going to write it on the board, though. So this is F, T, F, T, F, F, T, T. And now we just have to form the or of this statement. Not P or not Q. So that's F or F, T or F, F or T, T or T. These are the same thing, which means if I did the last step here of this and then bidirectional this, we're going to get T's all the way down, right? Because these are the same. We'd write a T, same, same, same. So let's take a look at what the intuitive idea would have been. And we'll see it's not even close to the same truth table. So not P and not Q. F, oh, well, that agreed. F, F, T. It's not even close, right? These two are completely different. So the point is, the sort of intuition there is incorrect. Yep.
Why do the or and operations swap when negated?
If we think in terms of English, is ultimately what it is. So let's just think. What's an example? Travis teaches in this room, and Travis is 36 years old. So that's a true statement. So let's say you were to form the denial of that. So you were to negate that. It would be Travis is not. It's actually a bad example. I have one further in the notes, which is helpful. So let me just say, hold on to that thought. We'll talk about it. But ultimately, another answer to that question is, well, if you form the truth tables, this is the correct one, right? So if you try the try not swapping it, you get not the same truth table, but when you try swapping it, you get the right truth table. And honestly, historically, that's probably how De Morgan, he was a mathematician, that's probably how he figured it out, was he was just writing them down, and he was like, oh, well, hey, I'm going to spend 10 years talking about this and get a research paper in the 1700s. Hooray. It is significantly harder to publish a research paper in mathematics these days. Okay. As an example, so I just went and looked for it. I don't like chocolate or vanilla. Right? This is plain English, right? So that's a statement. I don't like chocolate or vanilla. So is the same as I don't like chocolate and I don't like vanilla. Right, so I just went and dug up the example from the notes. So we can see here, this is not, I don't like chocolate or vanilla. Right? I don't like chocolate or vanilla. I don't like chocolate and I don't like vanilla. Right, so even in plain English, that's sort of how we talk, right? If we want to, sort of split this statement up into its two pieces, we swap the or to an and or the and to an or, right? So yes, this matches the truth table, but in terms of plain English, it also matches how we communicate. So another example using math would be x is not between 2 and 3. So in symbols, so x is not between 2 and 3. So that sounds like it's the negation of something. What is it negating? What's it not? X being between 2 and 3, right? So that would be x is bigger than 2 and x is less than 3. Right? Because we're saying x is between 2 and 3, right? Well, we're saying it's not between 2 and 3. Okay, so this is the same. So the De Morgan's laws well, we can distribute this sort of negative sign in there, right? It would be not or not like that. So we can actually think of what this negation does here, right? It's saying, so this is x is less than 2. So if we said not that, it would be x is bigger than or equal to 2, right? We flip the sign, right? So this is the same as we reverse the sign because we're saying, hey, it's in a sense the opposite of what you have written. Like that. Okay, so what's this saying? This is saying x is bigger than or equal to 2, or x is less than or equal. I think I have my symbols backwards. Hold on. I think this should be the other way around. No, that's right. I'm having self-doubt. I'm like, is this a typo or is my brain short-circuiting this evening? Which it can happen. Yeah, there it is. I didn't copy down the right symbols. Writing is hard. So now we flip these. Right, the point still stands. We flip the symbols. So what this is saying is x is less than or equal to 2, or x is bigger than or equal to 3. So this is saying x is less than or equal to 2, or x is bigger than or equal to 3. Again, we see these are the same statements, right? X is not between 2 and 3. So that means it's something that's, not sandwiched between 2 and 3, which means it's either 2 or less or 3 or bigger, right? One of those two things. Okay, so there are also versions of these quantifiers there's De Morgan's laws for the quantifiers. So how does it interact with them? Well, if we have the negation of for all x, p of x, this is a bit weird because the same thing happens. We switch the signs, right? So this is going to become there exists an x such that not p of x. And the same thing for the other way around. Not p of x. So what this is saying is if you want to negate for all x p of x, you have to say there exists an x such that not p of x. So let's think of, again, in terms of plain English, because just like with the other one, it's like, well, why did the symbols change? So let's consider a plain language alternative, I guess I could say, just to explain it. So suppose x is from the set of cars. So it's some car. It's your car, maybe. Unless you own a weird car, in which case it's not your car, it's someone else's car. So if p of x is x has four-wheel drive, then the denial of every car has four-wheel drive is, well, so this is going into like logical arguments. If I said every car has four-wheel drive, how would you disprove that? Your car doesn't have four-wheel drive? Yeah, exactly. You would say, hey, no, mine doesn't. So there's at least one that doesn't. So what you just said isn't true, right? So the denial of this, every car has four-wheel drive, is there exists a car that does not have four-wheel drive. There exists a car that does not have four-wheel drive. Right, so that sort of matches this, right? We're saying every car has four-wheel drive. If we want to form what's called the denial of that, right, the sort of counter argument to that, we would say there is a car that does not have four-wheel drive, right? And an example of the other way. So now suppose P of X is, what did I use here? X has three wheels. So I guess that's a trike or something. Whether or not we're calling that a car is up to debate, but I guess that's the idea. So the denial or counter argument for there is a car with three wheels So if I said, hey, I know of a car with three wheels, how would you disprove that? If I said, hey, I know of one.
By saying that all cars have four wheels.
Yeah, right, exactly. You would say, no, there are no cars with three wheels, right? So for every car, it does not have three wheels. So in other words, for every car, the car does not have three wheels. So there's something I kind of want to mention here, and it's really easy to confuse the denial with something that is stronger than that. And if you watch high school debate club, people like that make this kind of mistake all the time. And it's that the denial of something is not synonymous with the opposite of something. So let's look at this. So I said every car has four-wheel drive, right? If you want to disprove this argument, it is sufficient to just say, I found one that doesn't have four-wheel drive. Like, you made a strong claim. I've offered a counterexample. What are you going to do? So what will often happen is someone will say, every car has four-wheel drive. And then another person will be like, no cars have four-wheel drive. That's the opposite statement, but that's not a counter-argument, right? You are both now making equally strong claims that require a lot of evidence to disprove, right? So every car has four-wheel drive. If you want to disprove that, you just say, I found one that doesn't, right? But if you say, no cars have four-wheel drive, then you just also look like a fool, right? Because this person is saying every car has four-wheel drive, and they probably know of one that has it. So if you say no cars have four-wheel drive, they'll be like, what about that one? And now you just look like a fool, right? Same thing here. So, well, this one's hard because of words. Let me try to think of one. Examples would be all people are tall, right? The opposite of that is no people are tall. No, you would say there is someone who isn't tall. If you'd say there is a lawnmower that does not run on gas, right? The opposite of that is all lawnmowers run on gas. Like, no, there are electric lawnmowers. So if someone said there is a lawnmower that does not run on gas, your job to disprove that would be no, there isn't. Right? There is no electric lawnmower, and I can prove it to you, which there is. But like, the point is, you have to not get these confused with each other, right? If you say the opposite, you are saying a stronger thing than the denial of it. And again, it's just like the stereotype is like high school debate club or just any debate ever, where people are just arguing in circles with each other, right? And it's because they're doing that usually. It's because someone will say, every car has four-wheel drive, and the person will say, no, they don't. No car has four-wheel drive. And now they're just arguing in circles about whether or not a car has four-wheel drive. And it's like, this statement is disproved simply with mine doesn't. And then the person would be like, oh, well, shit, right? That's really all you can say in those situations. So it doesn't really, it mostly matters for the context of just mathematical arguments, right? Just if you're writing something down, if you're claiming something is this strong, then either you need to have good evidence for it, or you should consider the denial and be like, does that lead me to something that means I'm wrong, right? So if I said every car has four-wheel drive, I would think, like, if that's what my claim was, I was trying to prove that, I would be like, well, is there a car that doesn't have four-wheel drive? And I mean, this example is like, yeah, a lot. I would say if you're talking about just a car, like a hatchback, it probably doesn't have four-wheel drive. So, you know, if you're talking about a stronger mathematical statement, like what would be an example, like from linear algebra? Every matrix is invertible. If you don't know what that means, don't worry about it. But like, it's a mathematical statement, right? I'm making a claim. Every matrix is invertible. So if I wanted to, you know, think about that, I'd be like, well, is there one that isn't though? Right? Because I would start thinking of the denial of my own statement. If I'm trying to prove something is true all the time, I should think, what happens in, I don't want to say the opposite case, but that kind of is what it is, right? If I think about the denial of my statement, well, what happens in that situation? So it just kind of gets the gears turning, I would say, right? You just got to think about it. So a more math example. Is for every x squared is positive. So there's the denial. There exists, or there is, some x where x squared is not positive. Right? And so this is going to sort of the opposite situation, right? Here, you know, when I was saying every car has four-wheel drive, you just be like, well, no, right? But in this case, we're starting with something that actually is true. And so if we go down this route, we say, well, let's consider the alternative situation. What's that? There is some x where x squared is not positive. Then it's like, well, can't think of one, right? Again, barring imaginary numbers, right? I squared is -1, which is a negative number. But if we're talking about real numbers, there is some x where x squared is not positive. You'd be like, well, that's really hard, right? I can't think of one. That doesn't mean this statement is true, but it gives you some decent evidence, right? Like if you start toying around with this and just cannot find anything, then it leads some support to your original statement. And that kind of is some good advice for math. And lets me go to quiz 1, which is, so I looked over quiz 1. There were no surprises. Which is good. That means I know exactly what we need to cover and when and that sort of thing. So you don't have to worry about it. It's good. Is just try stuff, right? If you're ever unsure. So like if I present something, or you have to try to prove something, or You've got a formula in front of you and you're like, is that true or not? I don't know. The best advice is literally just try numbers. Just plug stuff in. And it's funny because mathematicians really struggle with that. Like I have colleagues that they'll immediately start abstracting and start trying to prove things in the abstract, and it's like, well, just try some numbers. Which programmers don't usually have that problem, right? Because if you're like, what does this function do? You just plug in some inputs and you see what comes out of it, right? And you print it to the console and you're like, oh, that's what it did. But that's true for math too, right? That's not a programming exclusive thing. So if you're looking at an identity, so, is it true that, an example from the quiz, a plus x over b plus x is equal to a plus b? Well, one way we can check that is we just try some numbers, right? Try a equals 1, b equals 2, x equals 3, right? They're just variables. You can just pick numbers for them, right? It doesn't matter. You can just pick whatever you want. So this left-hand side is going to be 1 plus 3 over 2 plus 3. That's 4 over 5. Okay, that's what this side is in this situation, right? In our choice of x. What about the right-hand side? Well, that's it's a over b, so 1 over 2. Is 4 over 5 the same thing as 1 over 2? No, those are different numbers. So then in this case, we would say, no, that's not the case because, and this is what I mean about these quantifiers, they're there. We just don't write them. This is really saying for all x and y, or sorry, not y, and a and b, the following is true, right? That's what this is really saying, is no matter which choice of x, a, and b we pick, this is true. And that's the thing with formulas and identities and that sort of thing. We don't often write this down, but that's sort of implicitly there, because if we're going to have a formula or identity, we should be able to apply it in every situation, right? That's why we have it, right? Think of like trigonometric identities. Again, we're not going to do trig, at least not in a way where it's like high school, but like sine squared of theta plus cos squared of theta. Does anyone remember what that is? I'm just checking. It's 1, yeah. So this always adds up to 1 because sine and cos are basically the coordinates on this unit circle, and this is length 1. Anyway, doesn't matter. The point is, you would expect this to be true no matter what you put here, right? So this is what I'm saying is really what this is saying is for all choices of theta, the following is true, right? No matter what you pick. Same thing is here as well. No matter what I pick for x, a, and b, is this true? I just picked somewhere it doesn't work. There are choices where it does work. If you choose x to be 0, it works, right? But that's not the point. The point is the claim is that it works for all of them. So if it doesn't work for one, then sorry, you need to add some qualifiers here to make it true. So like if this only worked for positive choices, then this would be a false statement, right? It would have to work for all of them. So my best advice for math is to just try stuff. Just plug in numbers. And it seems to defeat your instinct. So in math, if unsure, try numbers. Just whatever you like. And this is an important distinction. If you try some numbers and it does not work, that means the statement is false, right? Because you've just found what's called a counterexample, right? You found a situation where it doesn't work, but this formula is saying it works all the time. So you're like, hey, you lied to me, right? You said it worked all the time, it doesn't. Let's say, though, you picked some numbers and it did work. Does that mean it's true? No, maybe you got lucky, right? Because, like I said, there are infinity numbers, right? You picked 3. That's a lot smaller than infinity, so try again, right? And then, hey, it worked again. For like, I did 1, 2, 3. So maybe don't use like, and this is programming debugging, right? If you chose 1, 2, 3 and it worked, your next instinct is 2, 3, 4. That's a bad choice, right? Because those are sequential. Maybe it works for sequential numbers. So then I would try, okay, what about -2, 5, and 7, right? Okay, that worked. What about really big numbers? That worked too. Now I'd be like, okay, it worked for 3 choices and they're all very distinct from each other. Maybe there's something going on here, and I would start exploring it more. So when you want to prove something is true, it's a lot harder than disproving something is true. But trying numbers can be strong motivation, right? It doesn't mean it's true, because maybe you just got lucky 4 times in a row. Lightning can strike the same place twice. But it's becoming way less likely, right? At that point, it's probably going to be some very specific situations where it's not true. And then maybe you just need to identify those and then just rule them out in advance. Again, programming stuff, right? This is an example of how to write good unit tests. The user will try 1, 2, 3, then try -2, 5, and 7, then try aardvark 5 and 0.1, right? Like maybe those aren't even valid inputs. Try them though, because users are stupid and they'll do that. So make sure that it still works. But that's kind of the idea here. It's just try stuff, right? And generally speaking on that, so like I said, everyone got exactly the questions right that I thought. Everyone got exactly the questions wrong that I thought as a group. I mean, individually, people did things better than others on certain questions and then vice versa on others. So like factoring quadratics, most people are like, I don't know. Good, because that means it's been a while since you've done that, which is good for me, because if it weren't, then, well, it means you're very fresh out of high school and remember a lot of that. Another example is the last question, which was like solve these systems of equations. A lot of people like played around with it and had like the right ideas from high school. We're going to talk about that and come up with like quote unquote better ideas. Another one that is always funny to me, not because it's bad, but the long division one, the like doing long division. Most people are like, I don't remember how to do that, because if you even did it, it would have been in like 4th grade, 5th grade maybe, and then after that it's like just use your calculator. So it's like I'm really asking people to dig back there. So most people didn't, but the reason why I bring that one up is because there's an algorithm for it, and it's kind of interesting to think about, how would I implement an algorithm that does this sort of thing. But yeah, again, no surprises, and for the most part, there's nothing in there that I'm gonna like. We'll cover everything we need. That's all I have for now. So on Wednesday, we're going to spend a bunch of time doing some examples of why we care about this algebra, how we can do the algebra, simplifying statements, because you can look at it, and building a truth table for a really, really, really big statement is going to be annoying. So if we could simplify it first down to like something really small, now the truth table is really easy to see. So we're going to do some of that algebra, and then it'll be quiz time on Wednesday. So basically, Wednesday is going to be we're working on some examples, and then you work on some examples.